All right, let's get started. This section is section 6.2. Oops. It's on diagonalization. Well, before we launch into what that is, let's just review what we were talking about last time. So last time, let me scroll up. We were looking at examples of computing eigenvectors. And, okay, where is it? Yes, we had eigenvectors, and we saw that the vectors that get scaled by a particular value lambda form a subspace, the lambda eigenspace. So that's what's going on here. The lambda eigenspace, that's the set of vectors in Rn that get scaled by lambda when A multiplies that vector. And we gave two explanations, like two proofs for why this is. And one of them was to just check the subspace criteria. Right, that's these two properties. These are the subspace criteria. The first one is closure under addition, under vector addition. That's the first one. And then the second one was closure under scalar multiplication. So whenever you have two vectors that get scaled by lambda, any linear combination of those vectors also has to be scaled by lambda. And so that's how we get this subspace of Rn, the lambda eigenspace. And the second thing we did to explain how you know it's a subspace is that you can also recognize that the solutions to AV equals lambda V are the same as the null space of the matrix A minus lambda I. And we went over in class that the null space of any matrix is a subspace. So that's another way of seeing how you know that you get a subspace. And it's actually important to know that this lambda eigenspace is a null space of a different matrix, A minus lambda I, because this fact is used to compute the eigenvectors. And so we looked at this example. So I have this matrix 3, 1, 1, 3. And then the eigenvalues are easy. You just find the characteristic polynomial and then find the roots. And then how do you find the eigenvectors for each eigenvalue? So for the eigenvalue 2, we just found the basis for the null space of A minus 2I. Right. We got this vector. And so the null space is one-dimensional, so it's just spanned by that one vector. And for lambda 2, you just do the same thing. We found this basis, and so the 4 eigenspace ended up being scalar multiples of another vector. Okay. And I just want to clarify that, when we're talking about linear combinations of eigenvectors being an eigenvector, okay, we mean for a particular eigenvalue. So we're not saying it's not true. So all the vectors along this blue line, for instance, and this green line are eigenvectors. But if you take, a vector like this, like that, this one that I'm drawing that's like in orange, and then add, say, this vector that's along the green line, well, the sum, right, the sum is going to be, I guess it's going to be here. And that sum is not scaled by anything, because it's not along the blue line, it's not along the green line. So here you have two eigenvectors, and when you add them, you don't get an eigenvector. Okay, but that doesn't contradict what we were talking about before. Before we were saying that whenever you have two eigenvectors for the same eigenvalue and add them, you get an eigenvector for that same eigenvalue. So for instance, that would be saying in this case that if you took two vectors on the blue line and added them, you stay on the blue line. And then if you take, a scalar multiple of a vector on the blue line, you stay on the blue line. That's basically what it's saying. Okay. So anyway, that was what we did last time. And now we're going to talk about diagonalization. But before we talk about what that even means, can I write a theorem about eigenvalues and eigenvectors? This should give some more intuition about eigenvectors. So let's say that you have an n by n matrix A. Okay, so let's say you have an n by n matrix, a square matrix. And let's say that you have a bunch of distinct eigenvalues. So if A is an n by n matrix and lambda 1 through lambda k are distinct eigenvalues, and so you have these distinct eigenvalues. I'm not saying that these are all the eigenvalues, but let's just say you have some eigenvalues. Let's say you have k of them. And let's say you pick for each eigenvalue an eigenvector corresponding to it. So and v1 through vk are eigenvectors of A that correspond to the lambda i's. So such that lambda I corresponds to vi for I from 1 to k. Then the vectors v1 through vk are linearly independent. So then this set v1 through vk is linearly independent. Okay, that's something we won't prove, but let's just take a look at an example to illustrate this. So going back to the example above, here you have this 2 by 2 matrix, right? 3, 1, 1, 3. And okay, let's say you take two eigenvalues. There's only two eigenvalues, 2 and 4. And if you take an eigenvector corresponding to the 2 eigenspace, right, with eigenvalue 2, so that would be along the green line, and then you take a eigenvector with eigenvalue 5, those two vectors are linearly independent. Well, of course, in the picture you can see that, if you take a vector on the blue line and the vector on the green line, those would be linearly independent. Okay. Now, are there other examples I can use to illustrate this? So let's say, well, let's just keep this up there, I guess. So for instance, let's say you have, let's just use a simple example. Let's say that you take this diagonal matrix, how about 2, 2, 3, 0. Okay, this is a 4 by 4 matrix. It's easy, this is a diagonal matrix. A diagonal matrix, remember, 0 can be a diagonal entry for a diagonal matrix. Diagonal matrix just means that all the non-zero, how do I put this? That all the numbers that are not on this diagonal are 0. Okay, and do you see what the eigenvalues are? Well, yes, of course. The eigenvalues are 2, 3, and 0. And do you see what the eigenvectors are? What's the 2 eigenspace? Two eigenspace. What's the basis for the 2 eigenspace? How can I write it as multiples of one vector plus multiples of another vector? Can you see how to do it without actually doing any computations? The 2 eigenspace is going to be, so what's going to happen is this, so this matrix is acting on R4, and the E1 axis will be stretched by a factor of 2, and the E2 axis will be stretched by a factor of 2. And so the 2 eigenspace is just constant multiples of this matrix, this vector, and constant multiples of that vector. And the 3 eigenspace is all constant multiples of what vector? 0, 0, 1, 0. Okay. And then the 0 eigenspace. Well, what's another name for the 0 eigenspace, by the way? 0 eigenspace. These are the vectors v such that a, v is 0, v. Well, 0, v is just the 0 vector. So the 0 eigenspace, we went over this before, but it's just the null space. And so what vectors get sent to the 0 vector? It's all multiples of 0, 0, 1, 4. 0, what am I saying? 0, 0, 0, 1. All scalar multiples of this vector. And you can see that if you take these vectors, these are all linearly independent, right? So this vector, these 2 vectors, so the theorem says that I have, one eigenvector for each eigenvalue. So I guess, maybe I can make this first vector my, v1, say, and make that vector my v2, and I make that vector my v3, that these vectors are linearly independent. Okay. So that fact plays a role in what we're going to be talking about. And can we go over now the definition of diagonalizable? So we say that a matrix is diagonalizable, so definition. A matrix, and again, we're only working with square matrices. A square matrix A is diagonalizable if there is an invertible matrix P and a diagonal matrix D such that A is equal to P times D times P inverse. That's what diagonalizable means. Okay, it might not be very apparent what this even means, but let's just take a look at the example. Yeah, let's actually we'll talk about something slightly different, and we'll see the connection between where this comes from. So let's say that suppose that A is a matrix, is a square matrix, say n by n, with n linearly independent eigenvectors. Okay, so let's say that you have this square matrix and there are n vectors that are linearly independent, and those are all eigenvectors. So A scales all those vectors. Now A might not scale those vectors by the same scalar, but those vectors get scaled by some scalar. So they're not vectors that just go, random places. They actually get scaled. Okay. They're not necessarily distinct eigenvalues either. I mean, it could be that, let's say n is 5, and maybe the first 3 vectors are scaled by 3, and then the other 2 vectors are scaled by 2, or something. So anyway, let's say you have something like that. Well, let's say, should I just give the general thing with eigenvalues? Let's give those eigenvectors names. V1 through Vn with corresponding eigenvalues lambda 1 through lambda n. And again, some of the lambda i's might be repeated. Right? So it might be the case that lambda 1 is the same as lambda 2 if v1 and v2 are scaled by the same scaling factor. Well, what would that tell you? So a v1 is lambda 1 v1, and so on all the way to a vn is equal to lambda n vn. Right? Well, what happens if I take those v1 through vn's and put them in a matrix like this, make them the columns of this matrix? So I have these eigenvectors are n, right? So I'm going to have n rows, and I have n eigenvectors, so I have n columns, so I have an n by n matrix. And what can we say? Is this matrix invertible? Do we know if it's invertible? It is invertible because I have n linearly independent eigenvectors, right? Linearly independent. And so the rank is n, so it's an invertible matrix. Okay. Now let's say that I do A times this. A is a n by n matrix. This matrix is a n by n matrix. Let's call this matrix, well, let's not give this matrix a name yet. Okay, so if you have A times this matrix, this is equal to, well, by definition of matrix multiplication, what's the first column going to be? The first column of this matrix is A times V1. And so on, the last column is going to be A times Vn. Right? That's how you multiply. That's the definition of matrix multiplication. Now, what do we know about AV1 through AVn? We know the V1 is an eigenvector with eigenvalue lambda 1, etc., all the way to Vn. So this is going to equal equals lambda 1 V1 through lambda n Vn. Okay, so this is a square matrix with columns lambda I Vi. And how can we write this matrix as, let's say you take those vectors V1 again through Vn, and you have this matrix. It's the same matrix as before. Now what matrix can I multiply this matrix by to equal this? It's going to be this diagonal matrix lambda 1 through lambda n. Because remember, when you multiply a matrix by a matrix on the right, you're taking linear combinations of the columns. So this, if I do this column by this matrix by this column, it's going to be lambda 1 V1 plus 0 V2 all the way to 0 Vn. That's just lambda 1 V1. Right? So this matrix, those lambda i's, those are my eigenvalues. Eigenvalue matrix. And let's call that D. And let's call this matrix P. P is an invertible matrix. So we've written A times, and this is P, right? So we've written A times P is equal to P times D. And now what's something we could do to get A by itself? We can multiply both sides by P inverse. P is invertible. And we can multiply it on the right. Of course, the order matters, right? So we get A is P, the P inverse. You see, so this matrix is diagonalizable. Because the way we define diagonalizable is that it can be written in this form. Okay. On the other hand, if A has this form, okay, so on the other hand, if A is PDP inverse, right, the form that we had above, where D is diagonal, then if you multiply, we can kind of go backwards. You can multiply by P on the right, and then you get AP is PD. And what would that tell you? So let's say that P is the square matrix with columns V1 through Vn. Well then, A times P is going to be A times this matrix. And so the first column is going to be AV1, and the last column is going to be AVN. So if P is this, then AP is equal to that. And what's PD going to equal? If, let's say, D is this diagonal matrix with lambda 1s through lambda n's, then P times D is just going to be lambda 1 V1 through lambda n Vn. So what did we just figure out? Well, we just figured out, so if AP equals PD, then AV1 equals lambda 1 V1 all the way through AVN is equal to lambda n Vn. Okay. So that means that if A is diagonalizable and it has that form PDP inverse, then the entries on D have to be eigenvalues. And the V1 through Vn's have to be eigenvectors that correspond to the eigenvalues. And so that's another way of thinking about the fact that A has this form, PDP inverse. It means that it has n distinct eigenvectors, right? So let's just write that down. So what do we conclude? A is diagonalizable precisely when A has n linearly independent eigenvectors. Okay? So for instance, let's go way back. Let's go back to this matrix, 3, 1, 1, 3. So we found two distinct eigenvalues. Is this matrix diagonalizable? Yes, because it has two linearly independent eigenvectors. Right? You can take an eigenvector along the green line and an eigenvector along the blue line. Those two vectors span Rn. Right? I have, in this case, n is 2. So do I have two linearly independent eigenvectors? Yes. So that matrix is diagonalizable. Now Now what about this matrix? This diagonal matrix. Is this matrix diagonalizable? Yes. As you might expect from the name, it's a diagonal matrix. And well, we already found eigenvectors. This time I have 1, 2, 3, 4 linearly independent eigenvectors. Okay. So going back to that example, the first one, three, 1, 1, 3. Can I just make sure it is 3, 1, 1, 3? I just want to make sure this is correct. Yes, 3, 1, 1, 3. This is diagonalizable. And how can we write it in the form P dP inverse? Well, D has to be the eigenvalues, and we found that the eigenvalues are 2 and 4. And the eigenvectors are the V1s and V2s. And we saw that V2 has to have eigenvalue lambda 2. So the second column has to be a 4 eigenvector, right? A vector that gets scaled by a factor of 4. And what's one vector that gets scaled by a factor of 4? 1, 1. Okay. And so here's lambda, so that's lambda 1, that's lambda 2. Here's V2. And V1, we need a vector that's scaled by a factor of 2, and we found it's negative 1, 1, right? Yeah? And let's just check. If you multiply this matrix by negative 1, 1, you get negative 2, 2. Right? Okay, so that's our matrix P. So P is negative 1, 1, 1, 1, and D is 2, 4. Of these little zeros here. And then this matrix on the right is going to be P inverse. And you could compute P inverse, but let's just leave it like that. Okay, so A is equal to this. And one thing you notice is that there are many different possibilities for P and D. So this isn't the only P and D that works. So other possibilities well, for instance, D could have a 4 and a 2, right? It's not necessarily the case that the 2 has to come first and then the 4. It could be the 4 and the 2. However, if you make it like this, then can you keep the same P? No, because V1 has to be an eigenvector. So if you're making 4 your lambda 1 and you're making this your lambda 2, then the v1 here needs to be a 4 eigenvector. So it can be 1, 1. But does it have to be 1, 1? No. It could be any scalar multiple of 1, 1, right? So you can have 2, 2. And similarly, you could, for lambda 2, you could take any scalar multiple of negative 1, 1. So you could take, you could take 3, negative 3. That will work. So you can have this. And now you see where this fact about the eigenvectors being linearly independent come from, right? Because we were saying that if you have distinct eigenvalues and you take an eigenvector for each of those distinct eigenvalues, that those vectors are linearly independent. And you need that in order for your matrix P to be invertible. Okay. Now we should do an example where the matrix is not diagonalizable to see what happens. So let's take a look at an example. This is a very typical example. Let's say that you take this matrix 2, 1, 0, 2. Well, let's see what happens. So first let's find the eigenvalues. Well, that's easy. Can you see why this is easy? Can I see right away what the eigenvalues are? I think the only eigenvalue is going to be 2. Do you see why? So this is an upper triangular matrix. I have a 0 here. Right? The 0. And so if you compute the characteristic polynomial, you're just going to get a 2 minus lambda. This is going to be a 2 minus lambda, and that's going to be a 2 minus lambda. And then when you take the determinant, because you have a 0 here, your characteristic polynomial is just 2 minus lambda in parentheses squared. So the only root is going to be 2. Okay. So there's only one eigenvalue. And now let's look at the eigenvectors. Well, okay, so we need a minus 2I. And that's going to equal 0, 1, 0, 0. Now there's only one eigenvalue to work with, right? And so remember, we need 2 linearly independent eigenvectors. But if you think about it, in order for A to be diagonalizable, but can you have 2 linearly independent eigenvectors? Well, we see that this matrix has nullity. What's the nullity of this matrix? 1, right? So the 2 eigenspace has dimension what? Has dimension 1. So remember, the dimension of the 2 eigenspace is the nullity of A minus lambda I. So the nullity is 1, and so the eigenspace has dimension 1. And if you think about it, I mean, this example is so small, it's just a 2 by 2 example. Another way to think about it, without even doing any computations, is that there's only one eigenvalue, 2. So in order for A to be diagonalizable, right, you need 2 linearly independent eigenvectors. But you're in R2, and how can you have 2 linearly independent vectors that get scaled by a factor of 2? The only way that can happen is if A scales the entire plane by a factor of 2, right? So, and the only way that can happen, what does the matrix A have to be? It has to be the diagonal matrix with 2's on the diagonal. So that's actually an easier way to think about it. It's a bit more, you have to think about, it uses some facts that you only have a two-dimensional thing to work with. But basically, if you only have one eigenvalue, right, in general, okay, so, sorry, I'm getting too ahead of myself. So the two eigenspaces dimension 1, which is not equal to 2, so A is not diagonalizable. Right. So in general, if A has only one eigenvalue, so I'll just make a parenthetical remark, one eigenvalue, and I'm referring to real eigenvalues, then A would be diagonalizable if and only if, precisely when A is just, so if the eigenvalue is lambda, the only way this can be diagonalizable is if A is the diagonal matrix. Because you need n linearly independent eigenvectors that are all scaled by lambda. Okay. So that's an easy example of something that's not diagonalizable. But it turns out that there is a test for diagonalizability. So one thing that we're going to be talking about is a easier way to tell whether a matrix is diagonalizable. And it has to do with the characteristic polynomial. So before we talk about that, we have to talk about this notion of a multiplicity of a root. So now we're just going to say some kind of general things about the multiplicities of polynomials. So here's some terminology. So, okay, where are we headed? So we want a test for diagonalizability. Meaning some criterion to tell whether a matrix is diagonalizable or not. And it turns out that it will be in terms of the characteristic polynomial. So we have to talk about some general notions about polynomials. So let's say that you have a polynomial So just forget all the characteristic polynomial stuff. We just talk about random polynomials. So let's say you have a polynomial and you have some root of the characteristic polynomial. Right? So when you plug in x0, you get 0. Well, in that case, you can write there's just like a theorem in, what's it called? I don't know what this is called, but you can factor out x minus x0. So you can write x minus x0, and you might be able to factor out, well, you can write out x minus x0 times g of x for some polynomial g of x, and g of x might also have x0 as a root. So if g of x has x0 as a root, you can factor out x minus x0 again. So there's going to be some power of x minus x0 that you can factor out from p of x. Like the most number of x minus x0s that you can factor, let's just call that e. So we can write p of x as x minus x0s to some power times g of x, and g of x 0 does not equal 0. It might be more grammatically correct to say that we can write this with g of x 0 not equal to 0. Okay, so that number e, that's called the multiplicity of the root x0. Right, so for instance, let's just do one example. Let's say that you have f of t is negative t minus 3 squared times t minus 4. Okay, so what are the roots of this guy? 3 and 4, and the multiplicities, so the roots are 3 and 4 with multiplicity so what's the multiplicity of 3? 2, right? Because of this 2. And this, and what's the multiplicity of 4? 1, because it's t minus 4 to the first power. So respectively. Okay, and then one more thing, because we have to wrap it up. So one more thing and then oops. So we say that a polynomial p of t splits if I'm just gonna abbreviate this instead of writing it all out. If p of t has the form p of t is, well, it's some scalar times t minus a1, t minus a2, all the way through t minus an. In other words, and so where c is a scalar and a1 through an are all scalars, are all real numbers. Okay, I don't want to get too heavy in the details, too heavy in the theory, technically it should say splits over the real numbers. But let's just use this. It splits if P of t has this form. So let's just do a quick example. So this polynomial t squared minus 1 is t plus 1 times t minus 1. So it splits. But if you have t squared plus 1, that doesn't split. Because you can't factor this completely. So another way of thinking of splitting is that you can factor it completely, and you're going to get a bunch of different factors. You have no quadratic terms at the end. Okay. Now it might be that some of these AIs repeat. So for instance, you could have t minus 1 times t plus 4 in parentheses cubed. This is also a polynomial that splits up like this. Okay, so we're going to talk about the criterion for diagonalizability next time.